All right, it's a great pleasure to welcome Geordie Williamson from the University of Sydney, who will be talking about miracles. Miraculous something.
Thank you very much, and very nice to see you all again. So I'm talking about this a recent work with Simon Rich that's on the archive and is here and currently being corrected. So basically, the idea is to explain the, to give a proof of the linkage principle in the representation theory of an algebraic group that passes through the geometric Sataki equivalence. And why we're interested in doing this is basically, so it's something that's annoyed me since I was a graduate student that I didn't know. So we have this geometric Sataki equivalence that explains that algebraic representations of a group G are equivalent to some category of perverse sheaves. But then you can look at some basic statement that you know and can prove algebraically, maybe perhaps with not so much difficulty, and you can ask, can you prove it on the other side? And you just can't. And so I think that our kind of geometric knowledge in geometric Sataki has kind of lagged behind our algebraic knowledge, which is why I'm very happy to have an approach to the linkage principle. So let me just start with some philosophy. So Beilinson-Bernstein localization, absolutely amazing theorem. We consider the flag variety of a complex semi-simple Lie algebra. And global sections provides us with an equivalence between D modules on the flag variety and modules over the global sections, which is identified with a central quotient of the enveloping algebra. And I want to point out three aspects of this, which will be totally different in the world of geometric Sataki. So the first thing is that the relationship is very direct. These two categories are equivalent via a functor that, via the kind of most obvious functor that you would guess. The second thing is that on the right-hand side, we have this central quotient, which is telling you that this equivalence is only seeing a block. And once, so for example, a block of category O or something like that, and once you have this theorem, something like the Lusty Conjecture is manifest in the sense that once you have this theorem and you want to understand simple modules for a Lie algebra over this side, it's clear what calculation you need to do on this side in order to understand things. So now I want to contrast that with geometric Sataki equivalence, which is, so this is an equivalence between algebraic representations of an algebraic group and a certain category of perverse sheaves on the affine Grassmannian with a convolution product. And here, all of these 3 points are totally different. So the relationship is very indirect. So the way that you prove this is via Tanakian formalism, and you can probably guess that the relation is indirect because on the right-hand side, we have the appearance of the dual group, which is kind of, if you don't have the geometric Sataki equivalence, there's kind of no way of defining it that doesn't pass through combinatorics. So we've got this indirect relationship. The block decomposition is opaque. And the analog of the Lusty conjecture in the setting is called the Lusty conjecture. And the Lusty conjecture, if you look at what it says, it seems to involve things to do with the affine Grassmannian, so some kind of affine Lusty polynomials. But until this work, there was no proof of the Lusty conjecture that passed through the geometric Satake equivalence. And so, whereas on this side, the kind of Lusty conjecture is manifest as soon as you have this theorem, modulo a calculation that you have to do that was done by Kajal and Lustig. On this side, it's not even really clear how to approach the Lusty conjecture. And the kind of dream is that a kind of geometric understanding of rep G passing through geometric Satake. Okay, so in the same way that we understand representations of Lie algebras basically automatically via the localization theorem, we kind of do it by almost by instinct now. I would like to have this as the fundamental kind of localization theorem for representations of algebraic groups. And then we start here and we specialize off and build our understanding based on this fundamental equivalence. So that's the motivation. Now I want to give the main tool. So there's two main tools, and I'll concentrate on one, which is this Smith-Truman theory. So equivariant localization. We have a group acting on X, and we relate stuff on X to stuff on the fixed points. And stuff might be integrals, Euler characteristics, cohomology, K-theory, etc. Or it might be even categories. So a basic example, which is very important for this talk, is that if, so Z mod PZ acts on a finite CW complex or finite simplicial complex, then, you know, one of the first things we learn in group actions is that Z mod PZ has only two different orbits. It either has a fixed point or it has an orbit of size P. And so what this tells us is that if we calculate the Euler characteristic of X, then we get contributions from the fixed points plus a whole lot of contributions from the non-fixed points, and these contributions are all divisible by P. And so the basic statement is that the Euler characteristic of X is equal to the Euler characteristic of the fixed points mod P. Okay. That's a lovely basic exercise in a first algebraic topology course. And so that I've attempted to illustrate on the right-hand side with this picture. Okay. So that's great. We don't like numbers so much in quacks. So we would like some categories. What's a homological perspective? So we can consider chains on X. Sorry, chains on the fixed points. And this sits inside chains on X. And the quotient is a perfect complex. So what that says is that if we form the so-called stable category, so if we take the KB of FP gamma mod, so bounded complexes of FP gamma modules, and we mod out by, so perfect complex means bounded complex of free So if we consider this quotient via modulo perfect complexes, then inside here, so the image of this, the images agree. Okay, because the cone is a perfect complex, which is 0. And
Can I ask a quick question, Geordie?
no, there's no questions. What are you talking about?
Is part of the statement that any pth multiple of a chain on X is actually like contracts to the fixed points?
Any pth
Like, are you doing chains over Z or are you doing chains over FP a priori?
FP.
Okay.
Yeah. Okay, so the images of chains on the fixed points and chains on X agree in this stable. So this is what people call the stable category or the singularity category. And the Grothendieck group of this is Z mod PZ. This is a nice little exercise. And so the statement that the images agree is categorifying this statement. So that's the very basics of so Smith theory. And Dave Truman had the beautiful idea of upgrading this to sheaves. I remember when he first started working on this, and I was talking to him in Glasgow, and he was really excitedly explaining this to me, and I somehow wasn't convinced, and now I'm really convinced. So here we have Smith-Truman theory. So we have an algebraic variety with an action of Z mod PZ. And we consider the inclusion of the fixed points. And we can consider the bounded derived category of gamma equivariant FP sheaves. And now we have 2 restriction functors. Okay. And if you've worked with sheaves, basically, this is always annoying. Yeah. You might have some self-dual object here, but when you restrict it, the duality will exchange the stalk and co-stalk, and so this doesn't preserve self-dual objects and things like that. So it's important to note that gamma equivariant sheaves on a space with trivial gamma action is just equivalent to sheaves of FP gamma. Sorry, I don't know why I've changed to lambda here. This should be FP gamma modulus. Okay. And now we have this key lemma of Truman. So you have this canonical map from shriek to star, and the cone is perfect. And so that leads him to make the following definition. Smith of X gamma is this derived category modulo complexes with perfect stalks. So this is probably one of the most important definitions in this talk. Ooh. And so the point is that when we project to this Smith category, this is just the quotient functor, then these two, I shriek and I star, because we have a canonical map whose cone is perfect, so that cone becomes 0 when we project, and we get this miraculous Smith restriction. Functor. And Truman's meta theorem is that this functor commutes with everything. So Michael asks, is this a biadjoint in the statement? And I don't know what should be a biadjoint in the statement, so I can't answer the question, I'm sorry.
So I guess I meant whether in the stable category, this functor will have a left and right adjoint, or some kind of, if it is a joint functor. I mean, think are these left and right adjoints to some functor going the other way, or not? If not, then just ignore my question. If there is no,
let me say that sounds right. I'm not sure, but that does sound.
But
like
if there is a functor I lower something going the other way, then maybe you're just saying that it has a biadjoint if you use a stable category on one side.
Yeah, no, that's exactly what's going on. Yes.
Thank you.
Yeah. So we have I lower star equals I lower shriek, and yeah, exactly. This restriction is biadjoint to that functor. Okay, and the meta theorem is really remarkable. Yeah, so I guess one should think about this. So I think about it a little bit like hyperbolic localization, which is a wonderful functor for actions of C star on spaces. And what we're thinking of is, rather than C star, which is something like a circle, when we take mod P coefficient, Z mod PZ is a bit like a discrete circle. And this is some kind of variant of hyperbolic localization. Okay. So now we have one slide for the experts. Just so that I can make correct statements later on. We won't actually use the Smith quotient. We'll use a variant called which we call the equivariant Smith quotient. And I think I proposed this definition last year in these CDM notes for the CDM in Harvard, which is, so that it's very beautiful, this Smith quotient, but it has various deficits. For example, one of the most annoying things is that in this quotient, if you look on a point, then K maps to any shift of itself. And what we do is the following variant. We assume that the action extends to an action of C star, and we do this Smith quotient equivariantly. So we look at sheaves on the fixed points, equivariant sheaves on the fixed points, and quotient by the full subcategory generated by those sheaves whose restriction to mu p inside C star is perfect. Okay, so we replace mu p, Z mod pz by mu p, reasonably innocent, and then we impose an equivariance condition. And I guess an important thing to notice in this definition is that we really need that this mu p action extends, which of course it might not always do. And for people that love DG algebras, I think that this is a really nice way of thinking about this Smith theory. So one of the basic results in Bernstein-Lunz's book on equivariant sheaves is that the derived category of C star equivariant sheaves on a point is equivalent to the DG modules over FPX, where this has degree 2. And what does passage to the Smith quotient mean in terms of DG modules? It just means we localize this, this degree 2 parameter. Okay? So you can really think about this Smith category as being a localization of our category. And this has the wonderful consequence that, which is basically why we use this variant. So xi in the Smith category of a point of the constant sheaf with itself is 0 if I is odd and FP if I is even. And the reason that we love that so much is that, so there's this whole theory of parity sheaves, and it's somehow a very soft theory. all you need is some kind of parity vanishing, and then you can turn the handle. But if you don't have parity vanishing, then you're in trouble. But here we have parity vanishing, so parity sheaves make sense. And again, the idea to kind of pursue parity sheaves in the setting of Smith theory is due to Leslie and Lonergan. Okay, so a few more minutes before the first break, or the only break. I just want to very briefly go over the linkage principle. So basically, this Smith theory is this Treumann-Smith theory, Smith-Truman theory is the theory that we'll use, and the problem that we'll apply it to is the linkage principle, and I want to go over that briefly. So here's a picture of what algebraic representations of an algebraic group is meant to look like. So we have a split reductive group, Borel subalgebra, maximal torus, have the character lattice, and just as in the characteristic zero theory, for any highest weight, we have a simple module. And
except for one.
Except one, yeah. That's a very, very strange peculiarity for SP4, that 2 times one of the fundamental weights does not occur. No, sorry. Of course it does. So each of these blue dots, you have a simple module, just as in for a compact Lie group. However, their structure is rather different. So they're much smaller in general than, so apologies about that. I've just been signed out of my Zoom. No idea why.
You're still talking as far as I can tell.
Ah, okay, great. Okay, so all appears to be well. Okay, so this is our picture of what the representation theory of an algebraic groups look like. So if we're in characteristic zero, then this is a semi-simple theory. And all of these modules just look like for a compact Lie group. But if we're in characteristic P, then there's rather complicated behavior, which we still don't understand entirely. And this is just a picture of what the linkage principle looks like. So this is describing the blocks of representations. So I guess all I really care about, either you've seen this before and this is just a totally obvious slide, or you haven't. And what I want you to take away from this slide is that we have an affine hyperplane arrangement, which is these kind of yellowy orange, not quite sure what that color is, hyperplanes. These determine the action of a group, which is called WP, W sub P. That's this group here. And this group depends on P. So basically its scale depends on P. And now if we look at orbits of this group acting on our weight lattice and we intersect with dominant weights, then we get a so-called linkage class. So an example of a linkage class is here we take the weight 0 and we bump it around with our group and we get all these red dots. And now what we look at is the full subcategory generated by simple modules of that highest weight. The other extremely important thing to note in this picture is the fact that the origin is minus rho. So there's this rho shift that is also familiar in representation theory and characteristic zero. So basically, so this is the linkage principle, and this kind of is the basic statement that we start with when we're looking at representation theory of algebraic groups. And this linkage principle has not been explained in geometric Sataki up to this point. And after the break, I want to explain how to see it. Yeah, so the linkage principle is we have a block decomposition of our category indexed by the reflection in this hyperplane arrangement, which is centered at minus rho and depends on P. So we'll have a break now, and just to let you know what working with Ben Elias is like, this was the Skype screen from a few weeks ago. And I spent the entire Zoom meeting rather scared. So I'll leave you with that. We'll have a 5-minute break.
Oh, wonderful. Let's convene at 1:31. Ask your questions, please. I think that color is ochre, by the way.
Okay. Are you sufficiently scared yet? Should I remove the image? Ben is nodding.
Please. It's just like my mental state. It reflects too much.
Geordie.
Yes?
In this Smith theory, and this is a mod P theory. So what happens if you do the mod P to the power and to a power of P, higher
So
power?
that's a very good question. Yeah, I think about it, and I don't really know what to say. It seems like a very interesting question. It's yeah.
There's probably some natural guesses there, but. I have a question, Geordie. So you're doing everything, describing things in terms of the group algebra of the cyclic group and characteristic P. And that's also naturally a Hopf algebra. And it sort of has two standard Hopf algebra structures, the one coming from the group algebra and the one coming from the isomorphic description as like FP x mod x to the P equals 0. Does this Hopf algebra, does this coproduct appear anywhere in the story?
I think very much the first one does, because we're modding out like a kind of tensor ideal in the.
Well, it's a tensor ideal for both. But I guess the different tensor structures, never mind. But it's the same subcategory. It's a tensor ideal for both.
Yeah, I don't know. I don't know if the other one shows up.
I mean, in the algebraic group characteristic P case, this affine translation, somehow that is coming from the Frobenius morphism, at least in Anderson's proof of a strong linkage principle. So, and do you see how the Frobenius structure and in this geometric Sataki?
So maybe at the end I can try to answer this. So yeah, this still doesn't answer this kind of. So there's this problem of describing Frobenius under geometric Sataki, which I've banged my head against a lot. Yeah, what this gives a functor which we suspect is isomorphic to Frobenius twist tensor Steinberg, which is this kind of magic functor that shows up a lot. But we still can't actually produce the Frobenius twist by itself.
Okay. And you did this for the linkage principle. I mean, the linkage principle. You see, in the algebraic group, there are the flag varieties, and corresponding to each weight, you have induced modules, but those are the special ones. Then you have the non-bundles corresponding non-bundles on the flag varieties, and their cohomologies, and this time you have very nasty cohomology modules. Do you have any sense in the geometric Sataki you can recover those, or?
No. Okay, maybe I should keep going.
It's a good time. Sure, go for it.
Okay, oh, I forgot to say, I feel a little bit guilty that I haven't been to any talks in this conference, but they've all been at kind of 1 a.m. So, yeah. But, you know, if you'd like to, you know, I'd love to chat after. Okay, so the affine Grassmannian. So there's, I hope that this is familiar to most of you. There's this amazing infinite dimensional variety associated to the dual group. So we start with G, pass to the Langlands dual group, and consider the affine Grassmannian. And we get this infinite dimensional projective variety. And the geometric Sataki equivalence is this fundamental statement that the algebraic representations of G as a tensor category are equivalent to a certain category of perverse sheaves, of equivariant perverse sheaves on the affine Grassmannian. And here a simple module L lambda corresponds to, so the orbits of this group on the affine Grassmannian are naturally parameterized by dominant co-weights of G check, which is the same thing as dominant weights of G. And this equivalence matches parameters in the kind of most natural way you could imagine. And the remark is that this is not a derived equivalence. I mean, one possible remark you could make at this point that'll be useful later on is not a derived equivalence. So it's not true that dB of rep G is not equivalent to unless maybe your group is a torus. So now we come to probably the most important point in this whole talk, which is, yeah, thank you. Whoever, oh, so dB rep is dB perv, but this is not the niche where perv dwells. Okay, so one way of thinking about the affine Grassmannian is as being certain, as basically being a model for maps from S1 into the maximal compact in the dual group. So, and on such maps, you can just kind of rotate the map. And this corresponds in this algebraic model of the affine Grassmannian to just taking your parameter t and replacing it by zt. So there's this action of C star on the affine Grassmannian, which is called loop rotation, and is shown up in many different contexts. So I guess if you're familiar with affine Lie algebras, this is kind of the analog of the degree operator. So this observation that I remember Bezel Kavnikov told me when we were standing outside Kendall MIT stop in Cambridge in 2016. And I remember I was just totally blown away by it. And I thought, my God, like, I can't believe you've known this and not been proclaiming it to the world. But I kind of, it's one of those things where you feel like immediately you're going to be able to use it for many things, and then you discover that you can't, and then it sits in your brain for some time. So if we take the So one of the things that you do in kind of the first analysis of geometric Satake is just to take the fixed points of loop rotation. And what you get is a whole lot of partial flag varieties. So if you think about a geo orbit, it's a vector bundle or an affine bundle over a G mod P, and that base of that bundle is a fixed point under the loop rotation. So the moral of this is that the kind of fixed points under loop rotation are, in my opinion, rather boring. But if we look at the fixed points under mu P, hello. The last time I saw you, you were rather small. Fixed points under the mu P action, we get a disjoint union of partial affine flag varieties. And this is parameterized by the weight lattice modulo WP. Oops. Okay, so I'll show a picture in a second, but just two examples of this. So what this is saying is that so we have this, the fixed points are indexed naturally by the dots in the fundamental domain that appear in the linkage principle. And moreover, each of these components over here is a partial affine flag variety. Okay. So just two examples. So one obvious fixed point locus is what people call the Thin Grasmanian. So this is just, we replace the parameter t by t to the p, and we get a copy of the affine Grassmannian inside the affine Grassmannian that depends on p. And this is a kind of very interesting, rather thin. So if you think about this way, the way this sits inside the affine Grassmannian, it sits as a kind of, like it's a kind of small subvariety inside the affine Grassmannian. Another component is if we take gamma to be a p regular weight, then this component is an affine flag variety.
Can I quickly ask, Geordie, is there Langlands duality on both sides of that equality? So I mean, is G check on both sides of the equality there?
Yes.
Okay.
Yeah, there's no funny business with. This is all reasonably explicit geometry, so there's no swapping between G and its dual at this point. Okay. So, this is the kind of polemical slide. We have rep G, and we've seen this linkage principle. Okay. And so this is something that we would like to understand in terms of the affine Grassmannian, which is here. And now we take the mu p fixed points, and we have a decomposition into components which looks very much like, so for example, there's the same number of things on this side as things on this side. And they're parameterized by almost the same set. But there's a spot the difference here, which is maybe not so difficult, which is just to notice that the dot action is missing on the right-hand side. There's no dot action. But anyway, I think at this point, and this is what I thought back in 2016, that this looks all very suspicious. So this is just a picture of what's going on. So here's the picture from earlier with the row shift. So this is what's happening in representation theory. And this is what's happening in when we look at these fixed points, namely, so each of the dots in this fundamental domain index a component, and the degree of kind of partialities of the affine flag variety is governed by the stabilizer in the affine Weil group. So here we have kind of thin affine flag varieties. Here we have a copy of the affine Grassmannian, and here we have a partial affine flag variety along the walls. And here we have again affine Grassmannian, and here we have another partial flag variety. Okay. Yeah, so how on earth do we leverage this to understand the block decomposition? So I should say that at this level, you can still ask what restriction to these fixed points means in normal geometric Satake. And this was done by Leslie and Lonergan, and they relate it to a functor which is called Frobenius contraction, which is some kind of adjoint to Frobenius twist. But it's not really clear in the classical realization of the geometric Satake what these fixed points really mean, at least to me. What kind of really makes this story work is this second realization of the Sataki category, which is this Bezrel-Kavnikov-Merkovich-Gates-Risch-Rider theorem, BGMRB. Oh, I mixed up the order of, it's BGMRR. So we should have done a permutation here. So what this is saying is that we have this category of perverse sheaves on the affine Grassmannian, which is typically we think of equivariant perverse sheaves. But they explain that there's another realization of this as a so-called Iwahori-Whittaker model, which, yeah, I don't want to go into too much. You can think about this, probably like a first approximation of a way to think about this is, if you think about the Weil character formula, it says something easy divided by the Weil denominator is Weil's character. Now you can imagine taking the representation theory of G and just multiplying it by the Weil denominator. And suddenly you lose the tensor structure, but suddenly a whole lot of formulas become way easier. Yeah. And roughly passage to the Iwahori-Whittaker model is like multiplying by the Weil denominator. So you lose the tensor structure, but something that before was some very complicated standard sheaf with many complicated stalks, etc., just becomes something like an extension by zero or. So this is this Iwahori-Whittaker model. This is a really remarkable theorem. So I guess I have 10 more minutes, so I'll just go over a few remarks. So there's something, this is inspired by the Whittaker model, like Whittaker models in the representation theory of p-adic groups. So kind of magical things happen when you pass to Whittaker models. And you can't quite do a Whittaker model in the classical sense unless you're Frenkel, Gates-Grew, Vilonen or Lurie, and I don't understand that stuff. So we need to say Iwahori-Whittaker model, which is some baby version. We need, so in order to realize this Iwahori-Whittaker model in sheaf theory, we need some kind of so in the classical case, what we do is we take a character of an additive group. And so in order to categorify this, we need an Artin trilocal system. And so instead we should work over a field of characteristic L and use the Artin trilocal system. So from now on, we work over some field of characteristic, finite characteristic that's not P. So this BGMRR theorem is really beautiful. One of the so there's a number of things that just fall out of it immediately. One of the really interesting and nice things is that it does extend to derived categories. And the thing that we really care about is that is this thing that I put in blue. So IC lambda over this side goes to IC lambda plus rho over this side. And so what that tells us is that once we, like, basically, if we take IC lambda and IC mu over this side and we ask, do they extend? That's the statement that once we pass over this side, that lambda plus rho or mu plus rho are in the same connected component. Okay. So this is the main theorem. So here we have the, so we have this Iwahori-Whittaker version of sheaves on the affine Grassmannian. And we can look at Smith restriction. And this lands us in some Iwahori-Whittaker version of the Smith category. And basically the way that I think one should think about this theorem is as a localization. So this functor is just like, I imagine that my categories are linear over some polynomial rings, for example, and what I'm doing is inverting a parameter. And normally when you invert a parameter, you expect, for example, things to become decomposable that weren't decomposable before. So in a world that I love of Zergel bimodules, we often use localization and we'll localize a parameter, but when we do that, things split up. And the remarkable thing is that this particular corner of the universe is the kind of unique corner of the universe that I've managed to find in which localizing this parameter does not cause anything to split up. And so when we restrict this functor to parity sheaves, we get an equivalence with the Smith category. And so you can think about, like, the localization theorem in equivariant cohomology often tells you that, like, something embeds inside something else when you invert a parameter or something. And this is saying that when we invert a parameter, things stay exactly the same. And now we're on the fixed points, and so we can relate to many other worlds. So here I mean, this is telling you that each block is in a very direct way controlled by a partial affine flag variety. So a simple consequence of this, if we take two tilting modules on the left-hand side and we send them across this equivalence, they stay indecomposable, so they live on precisely one component. And if these components are different, then there's no Homs between them. And so this immediately implies the linkage principle. And it also implies, and one thing that I should emphasize about this whole stuff is that there's a little bit of theory making the Smith category work, and there's a little bit of theory making the Iwahori-Whittaker category work, etc. But once you have that stuff, the proof of this is a few lines. It's really remarkable. And so character formulas, which is something that I really care about. So this provides the first proof of Lustig's character formula for large P that passes via geometric Satake. So I was saying at the start, Lustig's character formula kind of cries out for a proof via geometric Satake. And I think when geometric Satake was first proved with modular coefficients, people thought that a proof of Lustig's character formula wouldn't be far away. It's kind of very direct. Another thing which is kind of exciting for Simon and I is, we get this character formula for tilting modules. So this is something that I spent a lot of time on. So in 2016, we conjectured a formula which involves these P Cauchy-Lutzyk polynomials. And we proved it for GLN using categorical actions of SLP hat, etc. So it was very much a GLN proof. And then with Pramod Achar and Shotaro Makisumi, we proved this via a kind of enormous journey through causal duality, which I understand now Maki and Matt can much better explain what's going on. But anyway, the proof of this formula kind of involves, I don't know, hundreds of pages. And it's for P bigger than H. So P bigger than the Coxeter number. And somehow, like with this Smith theory point of view, this just falls out like for all P, for all blocks, just straight away. Yeah, and thank you very much.
Thank you, Geordie. There is time for many questions, and I'm sure there are many.
Geordie?
Yes, voice?
It's Kaylin.
Oh, hi.
So is there an analog of BGMRR for affine flag variety?
What would it mean?
So, okay, maybe is there a Hori-Whittaker model for affine flag variety?
No, but I guess like it's really crucial that there's some, like the affine Grassmannian all involves some degree of partiality. So the affine flag variety involves no partiality. So when you impose a kind of Whittaker condition, you kill some things. So I would say that there's no kind of Iwahori-Whittaker model for the affine flag variety.
Geordie, does your proof extend to quantum groups at roots of unity case? It seems like you need coefficient to be a FP or over characteristic P field.
Is that Chio?
Yeah.
Hi. So that's a great question. So it's crying out for a proof. So basically, we should work on this. So there is a kind of Iwahori-Whittaker model for the quantum group that's been done by Gatescrew, where you work on the determinant line bundle and you use like zeta monodromic sheaves. And there should be some version of this, and it's kind of, I think it's really crying out to be done. But yeah, I don't think anyone's done it. And if you want to do it, you might get there first.
Logan just asked a related question in chat, and I guess I'll elaborate. Is there, like, with singular circle bimodules, is it obvious how to reinterpret the Iwahori-Whittaker version of things in terms of singular circle bimodules? And is there an expectation that it would quantize using my Q deformation?
Okay, so I'll answer the first question first. I don't think I need the screen, so I'll stop this. Okay, so so basically the way to think about these Iwahori-Whittaker categories in kind of Zergel bimodule land is as like a kind of, as a quotient. So like the antispherical module is something like an induction of a sign character. And the spherical module is induction of a trivial character. And so we think about like singular bimodules as being like a spherical module, and these kind of antispherical quotients as being a antispherical module. So what I suspect you can do is form kind of an anti-spherical quotient of singular bimodules in the context of geometric Satake. And this should give you the kind of Iwahori-Whittaker model. And then I guess this should also work with your Cartan matrix.
Thank you.
Geordie?
Yes?
So with this, still I'm thinking of the question I asked earlier, but this high power of P. So still with the coefficient still in the field of with the characteristic P, but the action, the circle action, you can have a higher power of P. Lusty in his paper on this generic Hecke algebra decomposition paper tried to describing in the affine, some affine planes and the transformation. Those are all just the kind of a transformation by multiples of P, or could be the powers of P. So if you change that, can you somehow do some kind of comparison with the in the Hecke algebra version in that paper?
Which paper do you mean, the generic decomposition patterns?
Geometric generic decomposition pattern on Hecke algebras. It's called a generic Williamson decomposition pattern.
So, yeah, so I know and love that paper, but I don't see the relevance of higher powers of P in that paper.
Well, basically that's which you can also work. I mean, that formulation works for you. You can translate the integral, the weights by multiples, by any from any multiples, not just the prime yes. multiples. So for quantum groups, you can take the L, and you can also take the. In particular, my main interest is take the L to be the P to the R power. So yeah. that fits into this circle rescaling action you mentioned.
Yeah, I would have to say I don't know. It's a good question if you can kind of understand this genericity.
Definitely, that's from this geometry.
The sound cut out there.
Yes, I just when I talk, I just use a space bar. So when after I finish, I mute myself.
I think this is a good time to thank the speaker, and then we can stay around and ask more questions afterwards.